We're far away, it's quite okay, like night and day, of endless grey, of what we used to be carefully. Now our undone deeds speak softly of how we used to see these unspoken dreams faded to modesty. We're haunted by our living shadows, our lifeless or loveless histories. They seek and speak when we're weak and blind our mind from our own kind. We love to need and we need to bleed the tears they set us free. We fight without a sight of enemies. This broken world carries our vanity in its heart. Like a mother we steal from, but keep in the dark. As we seek the happy, hungry, thirsty, horny, so much fear, unspoken tears. Years lost to ignorance, lives locked into destinations. Who really cares of anything here when the cry is weak and the fighting is strong? I fall in love with a tear of an old man. The 10,000-year puberty of the human mind. No collective consciousness better cool than kind. The need to have to go to endlessness of emptiness. I fill the void and feed my mind with your unanswered questions. Eyes that I've seen, not only watched. Ears that I've listened, not just heard. A mind that has been drunk on love Welcome, everyone. Amazing to see you all here. We are Phantom, and we're going to play 2 more songs, and then let's begin the real stuff. Dance me very gently. Let me closer slowly. Hold me till the morning. Move me to the beat of your silent love, and dance me to the break of dawn. Let me see your beauty in the darkness of your heart. Let me feel you moving in the fortress of your arms. Let the rain wash through us, let the darkness light us up. Dance me through the break of dawn. 'Cause the world will forget us. Will forget us. Take me to your solitude, to your unwitnessed truth. I'm not afraid to take you to. Touch me with your naked heart and break me apart. Let us love before we're gone. Let me see your beauty in the darkness of your heart. Let the rain wash through us, let the darkness light us up. Let me touch your kisses and the kisses fall apart. Dance me to the break of dawn. 'Cause the world will forget us. Yeah. Will forget us. Dance me very gently. Let me closer slowly. Hold me till the morning. Move me to the beat of your silent love. Dance me to the end. Dance me to the break of dawn. To the break of dawn. Thank you. All right, this next song, I have to say a few words, just because I made this song for my brother, actually, many years back. My brother got hit by a train, and he was really, really, as you can imagine, kind of a Frankenstein afterwards, but he made it. And now he works for CERN in Geneva, and he's one of my biggest idols in life and everything. And a few months back, I got a pre-brain stroke. It was pretty intense, and this is the first gig after that. And yeah, so I feel like this song is all about finding the beauty in the hardships in life, and I feel like we should really be more open and courageous in talking about these things. And I feel like if you're going through something bad, there's always someone for you, and that's what this song is about. Tricky heart longs for waves, the sound of distance, your presence stays, your words turn to gold, as physical fortunes can be sold. Phantom. Thank you.
Hey, thank you. I love Phantom. I love these guys. I especially love hitting the Helsinki karaoke bars with them because whenever Hanna is singing, everybody cries, and whenever I'm singing, everybody cries again. Good evening and welcome to Hack Talks. My name is Willi Miettinen, and there's a lot of familiar and friendly faces here. So a lot of you know me as a man with many hats. And tonight I'm going to be wearing two of those. First of all, I'm a board member of an entity called the Startup Foundation. And this is a very friendly non-profit mothership fostering startup activities here in Finland. Activities like Slash, Startup Sauna, Wave Ventures, Shortcut, and Junction. And then Junction is Europe's largest hackathon. About 1,500 people, hackers gathered here in Helsinki. It's starting tomorrow and lasts the whole weekend. And tonight we have in the audience quite a few hackers from Junction. Welcome. My second hat is that I'm the current chairman of ACM SIGGRAPH Helsinki. The first acronym ACM stands for Association for Computing Machinery, and it's the world's largest scientific and educational computing society. The second acronym, SIGGRAPH, is the special interest group on computer graphics and interactive techniques, and we are its local professional chapter here in Helsinki. And now we've been doing this event under the name SYysGraph. I believe this is the 22nd time. And this year we decided that ACM SIGGRAPH Helsinki should join forces with the people from Junction. And if I'm not completely wrong, I believe that tonight is the largest ever graphics seminar held in the Nordics. And we've split the event into two tracks. I think there is a total of 800 participants. In this track, in this room, if you came here to hear about web development, you're in the wrong room, please leave. In this room, what we should have are people from the industry, so both programmers as well as artists. We should have academic researchers, students, and hackers. Now, I would like to thank our sponsors. Slide. This wouldn't be possible without different sponsors, but I would especially like to thank Umbra Software, who are kindly trying to get us drunk tonight. So each of you probably has received 2 drink tickets, and one can be used here at this event, and there's the other one at an after party. And as all of you, of course, know, Umbra makes it possible to display arbitrarily large 3D data sets in real time on any platform. Okay, about tonight's program, we have 5 talks. We split them into 2 parts. So we start out with 3 25-minute talks. Then we have a break. It's a half an hour break. And then during the break, you can go to the bar. There's 1 bar. There's 2 bars in total, and there's restrooms next to the main entrance and upstairs. The break is exactly, here it says 25, but it's exactly 30 minutes. And then we continue with the 2 other talks, 1 25-minute talk and then a 45-minute keynote. And then at 10 p.m., we have an after party at the nightclub Maxine, which is a short walk or a tram ride from here. And now I would like to introduce my co-host tonight, the Master of Ceremony, Professor Jaakko Lehtinen. Jake is a long-standing member of the Finnish graphics mafia. He is a professor of computer graphics at the Aalto University and a principal research scientist, NVIDIA Research. Jake.
All right, thank you, Vili, for the introduction. So I'll be introducing tonight's speakers. But first, before we go on with the program, I'd like to thank the incredible team from Junction who are putting this all together. I couldn't imagine a more could not imagine a more professionally organized event. This is better than the annual ACM SIGGRAPH event, I have to say. I'm really, really impressed. So let's give a big hand to the organizing team. So Syysgraph, or Hack Talks as we call it tonight, has traditionally been a sampler of both the academic work coming out of Helsinki in graphics and interactive techniques, as well as talks about the interesting technical stuff that's the groundbreaking technical work that's going on in the industry in the Helsinki region. And we have a sampler of both types tonight. The ACM SIGGRAPH annual conference is the world's premier forum for disseminating academic work on graphics. And our first speaker, Dr. Timo Aila, is going to tell us about a new way of taking renderings that are noisy because they've been computed very fast and using neural network magic for cleaning them up. Timo, if you step up on the stage, please. Timo used to be, or was world famous in the demo scene in the 90s under the alias of Tsunami or Fairlight. His research for his master's thesis actually led to the founding of Umbra already about 15 years ago. Timo is now, world famous for other things, for instance, his research in fast ray tracing, and is no less than a distinguished research scientist with NVIDIA Research here in Helsinki. Timo, take it away.
Thanks, Jaakko. This talk is basically a reprise of our SIGGRAPH paper presentation from this summer. Behind the long and mysterious title, which is coming from the paper, is actually a very classical problem in computer graphics. If we're getting a stream of images that is extremely noisy, especially rendered images, how can we then turn it into something like this that is substantially more pleasing to the eye and temporally continuous? And we would like to approach this using neural nets because, deep learning solves everything, so maybe it solves this one as well. But before we start making our way towards the solution, let's remind ourselves quickly why there is noise in rendered images. So we have a 3D model with materials and everything. Light gets emitted from the light sources. It bounces around in the scene in many, many, many ways. And if we manage to take into account all possible paths the light can travel and connect them to the camera and integrate over those, we get a perfect image and there is no noise. However, if we can only afford to take a subset of those into account, in here I've taken 2,000 samples per pixel, and this is a trivial scene, of course, and all is well. But if we can take a very small subset, like one of them is horribly noisy, and why you would end up in this kind of situation, for example, if you're in a real-time regime where you have a strict 30 milliseconds per frame, then you cannot afford to take enough samples, so you will always be dealing with noisy images. Okay, let's start building our solution. We're first going to be having fun with still images and then proceed towards animation. For the purposes of this talk, an autoencoder is a neural net that learns to reconstruct its inputs. It has conceptually two parts, encoder and a decoder. The encoder takes the input image, it transforms or wrangles that into some internal representation, which it has learned, and from that it then reconstructs the image back. That said, I just told you that it does nothing. There would have been an easier way to return the input image, right? So why am I standing in front of 400 people and being all excited about a thing that does nothing? So sometimes there's a thin line between doing nothing and really quite a lot. And in here, the only thing I have changed is that I have corrupted the input image on the left by overlaying some annoying text on it. The intended output, however, stays the same. It's a clean image. Now imagine I have a substantial number of such image pairs, corrupted one and a clean one, let's say 10,000. Then I start training the network with this data set. What am I actually asking it to do? I'm asking it to first find out all the differences between the input and output. And once it has found those out, then go there and fix them. Fix the pixel color so that it seems like the text was never. This approach is actually really powerful and really general. You can remove text, for example. You can make it very specific so that only certain font is removed and not the other fonts. You can fix low light photographs with this. You can fix compression artifacts. And if you think about classical solutions to these kind of problems, every single one of them would have looked very different. And in here, the only thing I changed is the data. So you can reasonably say that in this case, data writes the algorithm. And this is also why this whole thing is sometimes called software 2.0. Now, before we go into example results, I'll provide a few details. Most details about the neural nets are actually not that relevant for the takeaway of this talk. What is relevant is that the network is fully convolutional, meaning that what we're actually learning are the convolution kernels themselves. And once we have learned those kernels, we can then go and apply them to images of arbitrary resolution. So we can be training with small crops and then apply them, just convolve images of any resolution later. The second important point is that the encoder, when it constructs this internal representation, it typically substantially reduces the spatial resolution of the image, which of course the decoder then reverts. But while doing so, it doesn't have to be, but in practice it does lead to very substantial compression. And compression means losing information, and therefore you would not be getting the same kind of image back as you would have lost high frequency detail. So the skip connections that I've marked here that connect layers that operate with the same resolution in the encoder and decoder, they rescue this detail. And other than that, training is just as with any normal neural network stuff. Now we're ready to show some results. So we have an image overlaid with some unwanted text. The task is to get rid of this text. The network has never seen this image, and it doesn't know where there is text and how much of it might be there. And from this, we execute the network, and it takes a few tens of milliseconds, and the text is gone. And this is a human face. We are really sensitive to, for example, it was on top of the eye, and we managed to reconstruct the eye really quite convincingly. Here is another example, perhaps a bit more challenging. There's more text. And again, the text is gone. What's interesting here is that if you look at the yellow bike, for example, there's Suzuki in there. It was not removed. It's a different font. There is Smith in the helmets. Was not removed. And if I go back, if you look at the red bikes, there is a large CR logo in the tanks, and under that is how many cubic centimeters. Can you tell? Computer can. 250 in both cases. Now you might nag that, okay, maybe it's not so difficult, it's always the same string we are trying to remove, and maybe there's not so much of it. We can turn it to 11 then. It is random strings. How many bikes do you see? Can you tell even that? Computer can. It's 7. And it manages to even reconstruct most of those spokes of the wheel. And of course, it has never seen this image before. And look at the Suzuki. It's almost an insult that it manages to rescue that. We can do other stuff. On the left, we have 10 out of 100 quality JPEG. It's awful blockiness. This is the kind of quality you sometimes see. And on the right, most of the blockiness is gone without introducing much additional blurring. We can take it again a little bit further. We can use 1 out of 100. And in here, it really has destroyed it. Most of the 8x8 blocks are just a single color. And this is the result we get from this info. It's quite remarkable that it manages to rescue the brown face from somewhere. I mean, there doesn't seem to be any information about that, but it still comes from somewhere. So hopefully by now I've sold you to the idea that these denoising autoencoders are really quite powerful for fixing images, and maybe, just maybe, they could be able to remove the kind of noise we have in rendered images. And they can. These are examples. On the left side of these images these are probably produced by using something like 500 samples per pixel. I'm just making that up, but it could be. And it's coming from NVIDIA's iRay product. And on the right side is after executing this kind of an autoencoder network. You could have gotten the same result, of course, but it would have taken several times longer. And of course, this is high quality offline rendering, so it already took a substantial amount of time. So it is of interest. Here is another example, and these kind of examples where the pixel values are almost correct, you could conceivably maybe apply it frame by frame to animation in, for example, computer-generated movies, and it might work. But that is not the case for real-time rendering, because the sampling density, the amount of noise is so aggressive there. But before I start explaining that in more detail, I have to specify what exactly I'm going to be talking about, because in real-time rendering, you always have to make severe approximations. So we are dealing with one-bounce path tracing. We start by rasterizing an image from the camera, and we store various attributes to a deep buffer called G buffer in the real-time rendering community. And these could include like pixel-wise distance to the camera and the normal vector, for example. We then continue from with path tracing. We shoot one ray towards one of the light sources, and we shoot another ray towards the scene, and then that hit point is connected to some light source. It doesn't have to be the same light source. And this whole contraption is denoted 1 sample per pixel in this talk, and all the remaining results are going to be about this. So we can still apply the same denoising autoencoder with this kind of auxiliary inputs as well. You just provide a deep image as an input. You just have additional channels in addition to the RGB. And what's amazingly convenient here is that you can just provide any number of channels you like, and the training of this network will then determine automatically which ones of them are useful and how to best exploit them, what kind of weights should be used for different ones of the features in order to best solve the problem we're trying to solve. And in here I have some examples about what kind of inputs are useful for this. The y-axis is the training loss, or the error remaining after going through this network. So obviously lower would be better. X-axis is the training progress. So obviously we expect it to get better over time, so we're hoping to have a downward slope. And starting, if we only provide a noisy color image, we get this kind of a slope. If we additionally provide depth information for each pixel, which indicates the depth discontinuity, so that's why you expect it to be useful, and it is. If we then also provide a normal vector for each one of the pixels, which indicate if it's a sharp corner or it should be interpolated across, that also is very helpful. Then we provide estimated roughness of the material, which in this case, which is a sponzacene, is probably constant or almost constant. So you expect it not to be useful, and it's not useful, but it doesn't hurt. So you can provide information that is not useful, and the training will automatically determine that it's not useful, and still be okay with that. Here is an example again. This is the kind of image we get by taking this one sample per pixel. It really is quite horribly noisy, and there's nothing there. And this is the result after executing the denoising autoencoder, which uses the auxiliary information. So from this to this. And many of you probably agree that this actually, it's not half bad. It's quite far from the reference, but it cannot possibly be the same. It has to be different in some way. The error has to go somewhere, if I go back and forth a few times. But maybe it would still work. Maybe it's still okay. But actually, when we run it in animation, it looks just plain horrible. There's a lot of mid-frequency flickering, and that's because there has to be error, and in this case, we process each one of the frames separately. So all of them end up making the error go into random directions. So we first tried to improve on that by using more than one of the previous frames. If you provide 2 or 3 previous frames, it actually improves the situation a little bit, but not enough. So we went into this recurrent denoising autoencoder thing where the recurrent loops that I've indicated with R, C, and N in the encoder, they introduce dependencies between the frames. So you can think about it so that I have a sequence of images, and I feed in the first one to the network. Then I have activations in each one of the layers of the network. Then I have introduce a feedback so that these activations are fed back to the same layer. And when the next frame comes in, I have activations of that, but I also have information about the previous frame. So they're no longer independent, which allows us to, so we don't actually have to decide what is in these loops. We just make it possible to pass some information, and the training will find out whatever is useful for solving the problem you're trying to solve. And since the frames are no longer independent, we cannot train with pairs of images. That actually sounds like it's not a big deal, but it kind of is a big deal in practice. And how we do the training is we first record fly-throughs in several scenes. And for each one of the frames, we produce, of course, the noisy input frame with auxiliary data and a noise-free target data. Then during training, we extract small snippets of these animations, 7 frames across, and take a small crop. And these are the small pieces of animation we're using to train the network. And in order to artificially amplify the amount of data, we also play the sequences forward and backward, and we stop the camera randomly and so on. So once we do that, these are the kind of results we get. So this is the input video. There's not much there. This is the previous best method, also based on deep learning. Still has a lot of flickering. And this is ours. Almost all of the flickering is gone in here. And again, side by side. It's still not perfect, but it's a large improvement over what was possible before. Here's another example. We are making this scene that have fully specular surfaces, meaning everything is a mirror. And the network training actually never saw fully mirror surfaces. So it's kind of a surprise that it produces something sensible even in such a case where it's forced to generalize quite heavily. So we are getting towards the end of this presentation, and the main message here is that we applied deep learning to light transport reconstruction. This one is running something like 50 milliseconds per frame at 720p today on NVIDIA Pascal hardware. This is getting faster really quickly. If you may already know that NVIDIA has shipped NVIDIA Volta architecture, and in that we have tensor instructions that theoretically speed it up by 10x already. So, and there is a race going on, and this would get accelerated by that kind of a instruction set. In the near future, we would of course like to make it faster still. Ideally, we would run it in 1 millisecond per frame so that you could really use it in a game. Of course, we understand that you cannot spend all of your cycles into this. If it takes 50 or 30 milliseconds, you would not really be able to use it. Quality, it's a large step forward. It's still not good enough in our mind. We would like to improve it further. If you have ideas, come talk to me. Further away, so far we replaced only the very last mile of a rendering pipeline with this deep learning thing, just removed the residual noise. Can we maybe think about methods to replace much larger chunks of the pipeline? And it may sound like, no way, there's, like, how would you approach that? But in a moment, Tero will present something that has no connection, no obvious connection to rendering, but still seems to strongly hint that probably, yes, you can actually do quite a lot. And with that, of course, a lot of people help with this, and I thank you for your attention.
All right, Timo, thank you for the talk. So we do have a couple of minutes for questions. The rules are, you raise your hand, you will be given a microphone, and only after you receive the microphone, you ask your question, okay? Do we have any from the audience? Oh, come on, don't be shy. There's one over there.
Yeah?
Hello. Firstly, thank you very much for the presentation. I have a question. Does it take less time depending on a degree? I mean, the more broken the image, the more time it takes, right? Or does it take the same amount of time?
It takes a constant time. It's a one feed-forward pass through the network.
Because I was wondering whether it would be possible in concept to use more than one sample per pixel, but at the same time less than 1024 pixels, and then maybe save time on that to get the same image as 1024 samples per pixel.
Are you talking about iterating the...
No, not iterating. I mean, in general,
I mean,
you said it's constant, but do you think it would be possible to make it variable depending on the amount of damage to the image and...
Well, you can train a single network to work quite well with all possible noise levels. For example, you can train a network that fixes all kinds of photographs regardless how broken they are. But the execution time of the fixing itself is still a constant process, in this architecture at least.
More questions? I think there's someone in the back. I'm seeing pointing at least.
Can you hear me? Oh, now it works. So thank you for the talk, and I have one question, but a more general. So the neural network structure shown really like it stores temporal information. Is it possible to transfer the same approach to the sound denoiser? And have you tried it for the sound noise removal?
We have not tried it, but I suppose, I mean, you really need the recurrent structure for that. I'm actually not knowledgeable about the audio denoising. I would imagine it works, but don't take my word for it.
There is a question right here.
Thanks. I was wondering if you guys tried using this on old, like really old video captures of back in, I don't know, when were the first video captures made?
You need training material. You need these broken frames, which would be the video you're talking about. But then you would need something to aim for. And basically you would have to probably do that synthetically. If you were able to emulate this brokenness of these videos, then it would work, I'm pretty sure.
Because I mean, you see some of these pictures and things, and they've been given life again, you know, after a long time given color. I was just wondering if that's a possibility, if you then take an old video and make some samples by hand and then use that as training material.
I think it's a realistic possibility. I mean, you just have to basically emulate the brokenness, breaking of this, or the noise in some way.
If I can add in, film degradation is a relatively well-known process that you can simulate. You know, you take a good image and you simulate what would happen to it if you left it, you know, if it was on a film and you left it there for 30 years. And then, you know, if you have a simulator like that, then you can train a model like that as well. One more question.
The last one, maybe. This is, of course, beyond, but nowadays we have a lot of scanning information coming from a variety of sources like laser scans and such, which might produce a lot of noise. This is not image-based per se, but could you theoreticize, like, could you apply denoising for a quick 3D spatial scans of similar fashion and maybe produce cleaner environment scanning results that way?
As long as the noise is deterministic, you can get rid of it. So I'm pretty sure that there's like nothing you have to do to get that working. It's just feed it in and it's going to work.
All right, let's thank Timo one more time.
Thank you.
Our next speaker is going to be Vinh Truong from Umbra Software. Vinh works on Umbra's 3D simplification, storage, AR, you know, you name it. They have really cool stuff going on. And he's going to tell us about their pipeline for taking completely massive 3D models and crunching them down into a form that lets you start looking at them on AR and VR devices anywhere in the world at the basically snap of your fingers. So Vinh, like most of us in the sort of the first wave of graphics in Helsinki, is actually a self-taught person. So lots of respect for that. It's great to see that similar zest is going on. Now, of course, it is possible for you to actually learn graphics from people who've done it before. So you should come study with me if you're interested. But Vinh, please.
Sorry about this setup. All right, so thanks for the introduction. So yeah, my name is Vinh. I'm currently a graphics engineer at Umbra, and yeah, I've been there for 3 years now, and during that time, I've been working on many of these techniques that I'm about to show you during this presentation. And hopefully also during the presentation, you'll learn what the title is all about. All right. So in this video, you see our app running on an iPhone. It's an AR app where you can view and interact with your 3D models. And yeah, the rendering feels smooth and a good quality. But in terms of experience, you can already find many apps and games that can already do this. So this doesn't seem super interesting by itself. Here's the same app again, but now we're looking at the city of Helsinki. The rendering still feels smooth, even though the scene in question is really big. But again, in terms of experience, there are many mapping services already that let you view large cities in 3D, and they do perform really well even on mobile devices. So to help you understand where I'm going with this, I'm gonna give you a bit more context behind these videos. So assuming we are rendering in 60 frames per second, the iPhone 8, which was the device seen in the videos, it can do around 1 million triangles per frame, given a reasonable setup. And that in itself is pretty impressive, actually. But as you can see, that's not even close what we actually need. You need way more iPhones to render these guys. And the same thing is true with video memory as well. So with these numbers in mind, how does people end up doing it? Because clearly they have a solution already, because otherwise there wouldn't be any content that looks like that. So depending on the type of data you're working with, you have two options. For example, if all your data kind of looks like the Helsinki model you saw earlier, you could create a specialized tool that just assumes that all your data is mostly flat, sort of like a height map at that point. And that's all good if that's all the type of data you're dealing with, but of course, as soon as you come up with something else, then you have to create another tool and start hating your life, and that's not fun. The other more common case is that you have skilled artists and level designers at your disposal, and they can ensure that during content production, the scene will always perform well on some specific set of target devices. And this obviously involves a lot of manual labor. So yeah, you probably already know where this is going. We at Umbra think that it's possible to create a generic enough optimization pipeline which can dramatically improve productivity in both of these scenarios. So here are some of the requirements for the system for it in order to be useful. We want the end results to automatically work on any target platform. So a single optimization pass should be enough to cover all the interesting targets we want. We want the solution to work with the scenes of any size. And we want the solution to handle anything from vehicles, buildings, and whole cities. And it should be generic enough to not assume pretty much anything about the data. Okay, so let's have a look at how the Umbra's magical solution actually works. So the main technique we are using is called level of detail, and it's a really simple concept to understand. All you do is you provide multiple versions or levels of the same object, where each successive level has less detail than the previous one. And then during runtime, you pick the right level of detail based on its distance to the camera, and that's all it is. This type of LOD is sometimes known as object LODs because each level is just the same object with less detail. This is in contrast to what Umbra actually does, which we like to call hierarchical spatial LODs. So spatial LODs, as the name suggests, deals in regions of space instead of individual objects. So here, everything inside the region is treated as if it was a single object. Everything outside the region is just ignored. And from this point on, I'll start calling these regions as tiles. So hierarchical spatial LOD is just the same thing, but in an octree. So every node in the octree corresponds to some region of space which gets treated like a spatial LOD would. One really cool property of this technique is that we can pretty easily bound the maximum cost of rendering the whole hierarchy at any camera position. So if you imagine we can assign a constant cost for every spatial tile we have in the hierarchy, like seen in the picture, you can kind of see how the total cost stays reasonably bounded no matter how the camera moves. So here's a quick animation of what that looks like if you haven't seen it before. You can kind of imagine that as the tile configuration changes, the rendering cost always stays nice and predictable. Okay, so now we have a solid foundation to work with. So let's move on to reconstruction. So why we do want to reconstruct anything? Because the LOD technique I just described has really tough requirements. Things like how the spatial tiles are arranged, how big they are, and how much data can they contain. And it's very unlikely for that the model submitted by the user can be used in this technique without significant modifications. So this is why we took the radical approach of basically creating a replica of the input model. And since now we get to control every triangle and every texel in the replica, we can guarantee that the replica model will fit perfectly into our LOD technique. So let's dive into the pipeline and see how the thing actually works. So we start by importing the model into our pipeline and then immediately start building out the LOD hierarchy. Once we know all the spatial tiles, we can just begin reconstructing them. And to make things simpler from this point on, let's look at a single tile. So let's start with meshes. To get some idea how Umbra's mesh reconstruction works, it helps to understand some of the basics first. So let's say you have a function that just tells you the distance to the nearest surface and also if you're inside or outside the surface. This is known as the signed distance field. And your goal is to find the surface where every point on the surface are the zeros of this function. And this type of surface is called an iso surface. You can find zeros of this function multiple ways. One way is to do a binary search, basically. You just find 2 points where when you evaluate the function at the points, the signs don't match. They have different signs. One is positive and one is negative. Then you just bisect your sample at the center, and then again find where the sign changes, and you continue like this until you find the zero. And to get polygons actually out of this, you just do the same thing, but in a square. So just sample all the corner points and find where the sign changes at any of the corner points. Once found, you just create your polygons by connecting the 0 points at the edges, like seen in the picture. Here are a couple more cases, and you just repeat this process in a grid, and that's basically how marching squares works. And of course, this extends to 3D as well, and that version is called marching cubes. You just have 8 sample points instead of 4. So you can get even better results by changing the rules a little bit. Instead of immediately connecting the intersecting points, you use the positions and the normals to find the vertex inside the cell by minimizing some error function. And the error function here is sort of like mean squared error between the placed vertex to the intersection points. And we get polygons by connecting the resulting vertex to other vertices in the neighboring cell, which are computed in the same way. And that's dual contouring. And our current implementation kind of resembles dual contouring with some modifications. We use dual contouring because it produces meshes with cleaner topology, preserves sharp edges, at least compared to marching cubes. Okay, so that's enough theory. Let's look at how it works. So here's what the initial reconstructed mesh, what it looks like. And Here's the same thing, but with the wireframes turned on. You can see how dense this mesh is when it comes out of the initial reconstruction. We're going to fix that right now. We are going to apply a series of simplification steps to get rid of the triangles which don't noticeably contribute to the mesh. This is called mesh decimation. I'm just going to show you a video of it in action. Yeah, it's pretty cool. I could watch this all day. Anyway, the decimation stops once the only choices remaining introduce too much error. So anyway, at this point, we are done with the meshes. This is the mesh that the user is eventually going to see. So next up, let's talk about materials. This is way simpler than the mesh reconstruction. The only goal here is to paint our mesh with some colors. So here's how we do it. Let's imagine that this part represents a part of the input mesh, and this is our approximation or reconstructed mesh right on top of it. We are going to put a ton of evenly distributed points on top of the reconstructed mesh. And from these points, I'm just going to start sampling the input mesh. And we do this by just casting tons of rays at every point towards the input mesh and see if we found any intersections. And for each intersection point we find, we're just going to sample the color at that point and then store it. And here's what that looks like. Yeah, I bet we are the only people in the world who paint cars like that. Okay, now we have our color data. To finish off, we have to create a 2D texture which represents all these colors. And we do this because the GPUs will thank us if we do it. So that process is called UV unwrapping. It's sort of like origami in reverse, where you start with the origami and end up with the paper. And yeah, we have built our own UV unwrapper to do this, and this is what it looks like. And yeah, no Ferraris were hurt in the making of this video. So that's our materials. We're just gonna, to finish things off, just repeat this exact same thing for every single tile we have in the hierarchy. And that's for reconstruction. All the tiles are now neatly packed up, so they can be shipped back to be consumed by our users. So to access the reconstructed model, our users have to integrate a tiny program called the runtime into their apps. In fact, there's not much to say about the runtime because it's really simple. Since all the heavy work has been done up front, the runtime's only job is to manage data transfers between the permanent storage and the GPU. And that's the whole thing. With all the stuff we have done so far, you can already go and use this setup to optimize your scene and get them running on your target device. But of course, we're not going to stop there. We at Umbra always want to add in some extra sauce to improve the results even further. So I'm going to go briefly through at least a couple of them. So visibility. We at Umbra, Umbra is best known for visibility since we have done this for like 10 years already. And we have shipped hundreds of games that include our tech. We have talked about visibility techniques before, so I'm not going to repeat those because the concepts are still pretty much the same. If you're still interested though, there's a lot of in-depth posts written about this. You just Google with terms like Umbra visibility solution if you want. In short, just generate a data structure which can really quickly perform requests like, from this camera position, give me the list of visible objects. And obviously we use this to improve rendering performance during runtime. But we have found other uses for it inside the reconstruction pipeline. So for example, the spatial lots I explained earlier, it forced everything inside it to be a single object. That was the whole point of it. But sometimes it's not the best thing you can do, because for occlusion culling purposes, it makes more sense to have smaller meshes to get more precise visibility results. This is a sort of trade-off that you can make. And one way we do this is we start looking out for regions which can never be seen at the same time from any camera position. We call this the reachability analysis. It sort of makes sense that if you're outside the box, you could never see actually the stuff inside it. So we can just separate the meshes, and as long as you're outside the box, we just never saw anything inside it. Just save a lot of memory and improve performance. So next up, lighting. One detail I kind of glanced over when I was talking about material reconstruction is that all the texels in our replica model are unique, meaning that every texel corresponds to some unique position in the world. And that's exactly what the light maps require. And since we already have them as part of our pipeline, let's make use of them. We can just bake ambient occlusion if we want, with no runtime cost. And might not sound like much, but some of our users submit scenes that are all white. So by just applying AO to their models is enough to like make them scream like little girls. If you don't care about dynamic lighting at all, you can choose to go even further and start tracing light paths to get global illumination, at least for the diffuse case. And yeah, this stuff is very much work in progress, so there isn't too much to mention. One thing that's definitely true about GI is how much time it takes to compute, which takes us to the magical cloud. And the third and final thing I want to quickly mention. So of course you can run our whole pipeline on your local machine, and we do during development. However, for large enough inputs, you need a lot more horsepower to get this job done. And of course, we get that from the cloud. Sorry. And since our tiles in the load hierarchy don't depend on each other, we can easily schedule them to run in parallel. For example, if the hierarchy had 1,000 tiles, we can just run 1,000 CPU cores to do the job. That is the main reason how this becomes practical for large scenes like Helsinki with its 2 billion triangles. I think I launched something like 500 CPU cores to compute that. So once you add in lighting computations, this is pretty much the only way to go. Our cloud has another important job, which is hosting the reconstructed tiles. With large enough scenes, even after reconstruction and all the optimization is done, the results can be larger than what the device can even store in its permanent memory. Therefore, it's more productive to stream directly from the cloud instead. So yeah, that's mostly what I wanted to say about the cloud. Before I wrap up, I want to mention a couple of things. So the obligatory "we are hiring" slide. So if you found this presentation interesting at all and you want to be part of doing this kind of stuff, you know where to find us. Our offices are right here in Helsinki, so you don't need to go too far. Secondly, the app you saw at the very beginning of the presentation, it's called Umbra Prism with the Z. You can thank our marketing lizards for that name. That's now available on the App Store. So if you have an iOS device, you can try it out for free. You don't need to sign in or anything like that. You can find the Ferrari and the Helsinki and a whole bunch of other scenes that I have put there. So yeah, there's no ads or in-app purchases or crap like that, so you don't need to worry about it. Lastly, I'm just going to give a couple of shout-outs to people who have been gracious enough to either help directly the creation of the presentation or providing great feedback and support. And that's all. Thank you very much for listening.
All right, thank you, Vin. We have time for maybe one quick question. All the speakers will be there during the breaks and afterwards as well if you want to chat about more technical details as well. I hear someone tapping the mic.
Yeah, thank you. One quick question about the tiles and the seams between them. If you have a big object that spans multiple tiles and they have different LOD levels, so how do you handle the seams? Like if there are polygon seams between them, how do you make them continuous?
Yeah, it's the short answer is that we do handle them, and the long answer is that it's really complicated. So I just left out the whole chapter. We do handle them. The seams are watertight, but I would have to explain a lot more about how the mesh gets initially reconstructed and the decimation and stuff like that to appreciate the seams.
So that's the secret sauce.
I guess so. Yeah.
All right. I think we'll have to thank Vinh and move on to our final speaker in the session. Like I mentioned, the speakers will be there during the breaks for you to chat with, okay? Our final talk before the break is going to be given by Tero Karras, who is a principal research scientist at NVIDIA Research here in Helsinki. And he's going to be, he's also world famous for extremely fast ray tracing and stuff like that. But he's going to be telling us about something completely different, about a new machine learning technique that we've put out there just a couple of weeks ago, and that's caused quite a stir in the machine learning and AI community by its ability to generate uncannily real images of people who do not actually exist. And Tero will tell us all about it.
Thanks, Jaakko. So, yeah, I'm going to be talking about this recent project we did at NVIDIA, and the stuff is currently under review for the ICLR Machine Learning Conference. We humans are fantastic creatures, because if I show you a picture, you can immediately tell that it's a cat. That's because we have deep understanding of what cats and other types of objects are supposed to look like. And some people can even use this understanding to create realistic, novel drawings of the subject. But what about AI? Well, in terms of classifying pictures as cats or other types of objects, we can say that modern machine learning techniques have pretty much already surpassed human-level accuracy. But do these techniques really understand what they are seeing? As Richard Feynman put it, what I cannot create, I do not understand. And it just so happens that when it comes to the creativity department, current AI techniques are kind of lacking. The basic problem is that of generative modeling, where you're basically given a bunch of material, like pictures, and you want to construct some kind of a model that you can then use to create more of them. Over the years, there's been quite a lot of different approaches to attack this problem with varying levels of success. But by far the most intriguing technique is generative adversarial networks, or GANs for short. It all started about 3 years ago when Ian Goodfellow and colleagues published this radical new idea of pitting two models to compete against each other. So we are talking about a two-player game, and let's say the first player is a bad guy who wants to create some fake money, and obviously the second one is then going to be the good guy. At the beginning, these players are kind of dumb, so the bad guy might produce something like this, and obviously it's not too hard for the second guy to tell that this is a fake. But now suppose the bad guy can actually read the mind of the other one, So they can know exactly how and why they concluded that this is a fake. This information tells them exactly what to improve, so they kind of level up and are able to produce something much more convincing soon enough. Well, the good guy is now puzzled. It looks okay, so they are forced to inspect it in detail, rethink what it is they're looking for, and that's forcing them to level up as well, so that they can ultimately tell that this one is fake as well. And so it goes. Both players keep pushing each other to better themselves until eventually we can imagine that they have reached a level where you see something undistinguishable from the real thing. So in practice, we of course represent these players as deep neural networks. We have the generator network, which is pretty basic. It consists of standard layers stacked together, and the input is what we call a random latent vector, basically just a bunch of random numbers, and the job of the generator is to turn these into a picture. Then we have the discriminator network, also sometimes called the critic, whose job is to look at pictures and classify them as either real or fake. To train these things, we alternate between training each of the networks. When we're training the discriminator, we start by first using the generator to create an example of a fake image, which we then pass to the discriminator network. And of course, we'd like the discriminator to be able to tell that this is a fake image. So we do backprop as usual and adjust the weights of these trainable layers so that the discriminator will be able to do a better job in the future. We also show it examples of real images from our training data and do the same thing. We want these to be classified as real, so we update the weights, and so it goes. To train the generator, the process is not that different. We again generate fake images and pass them to the discriminator. But now the goal of the generator is to actually fool the discriminator the best it can into thinking that these are real images. So we flip the objective and do backprop. This way we know exactly how the image should be modified to make it look more realistic. We continue backprop to the generator and again update the weights so that in the future the generator will be producing slightly better images. This idea has been kind of a big deal in the research community. Lots of people picked it up immediately, and you see all kinds of praise for the technique. But it's not entirely free of difficulties either. I'll give a typical example. Suppose you want to train the generator to produce images like this. Of course, at the beginning, before you have done any training, you get this random garbage. But once you start this alternating training process, the images pretty quickly turn into something quite reasonable. Then when you continue training, we can see that the results are not really getting any better. And in particular, there's much less variation in the generated images than the training data. So in a way, the generator has found a safe zone and is afraid to step out of there. If we continue even further, it always goes like this. Boom, catastrophic failure. One of the players wins, another one loses. That's the end of the story. And these difficulties are, of course, well known. And the consensus so far has been pretty much that it's a promising, attractive technique, but ultimately useless. So For our project, the goal was pretty straightforward. Let's fix them. Meaning we want to get high resolutions, bigger networks, better image quality, better everything, basically. That's not an easy thing to do. There are many problems that need tackling. First of all, we need some training data. We need to do something about those catastrophic failures. Training performance is also a concern. And we need to drastically improve the quality and variation in the generated images. And finally, we have to be somehow able to objectively measure whether we are actually improving the situation or making it worse. It's harder than it sounds. So let's start with training data. With GANs, there's been kind of a chicken and egg problem because the techniques have been limited to low resolutions and low image quality. So there has been no pressing reason to create any better datasets either. So we decided to roll our own. We took about 200,000 random celebrity images from the web, the same set of images that was originally used to create the standard Celeb A dataset. And then we applied all the image processing mojo at our disposal, including Timo's autoencoders, to enhance the image quality and filter out the bad ones, do high quality alignment to the facial region, and so on. And in the end, we got 30,000 really high quality images at 1K by 1K resolution. For additional validation, we also decided to use the standard LSAN dataset. The resolution is much lower here, but the nice thing is that we have 30 different categories of objects and lots of image for each category. It's also worth pointing out that these images are significantly more challenging to model than the celebrity faces because there's ridiculous amounts of variation in them. So we have data. What about the catastrophic failures? Well, the thing is that with a traditional approach to training, since we're aiming for really high resolutions, this means that the networks will be very deep as well. And at the beginning, we're initializing all the layers with random weights, meaning that neither of the networks, none of the layers have any idea what they're supposed to be doing. It would take an immense amount of training for them to get a clue, but by that time, the training will already have failed. So instead, we proposed to grow the networks progressively. We start with a really low image resolution of 4 by 4 pixels and tiny networks consisting of like 2 layers each. And then as the training goes, we gradually keep adding more layers, increasing the resolution until in the end we have reached the full resolution. And the point here is that at any point during the training, most of the layers in both networks already have a pretty good idea on what they should be doing, and we have only a few layers that we are training from scratch, which stabilizes the training process considerably. So in practice, the training looks like this. You can see it starts from a low resolution, and it quickly ramps up to higher resolutions. The image quality is improving pretty consistently. It takes about 10 days on a single Pascal GPU to reach the full resolution, and at about 20 days of training, the results are starting to look kind of okay. So just the progression on its own takes care of the failures. And as a byproduct, we also kind of end up solving training performance as well, because we are doing most of the training using these tiny networks, which are really fast. Then how about quality and variation? Well, for those, we propose 3 other techniques to improve the training, which I will not describe here. But the paper is publicly available, just Google for it, and you can read more about these from there. When we combine all 4 techniques, these are the kind of results we're getting with 20 days of training for the celebrity faces. So these images are exactly as they pop out of the generator. And as Jaakko mentioned, the interesting thing is that none of these people actually exist in the real world. We have tried to find the closest matches in the training set for many of these, and they look nothing alike. Many of the images are quite convincing, but there are a couple of failures, monsters in there. Surprisingly few, though. What's even cooler about this trained generator is that the GAN formulation actually forces it to be continuous. So if we think of every generated image as a point in the high-dimensional latent space, then if we have 2 points, we can just interpolate them, and the resulting images will interpolate smoothly as well. What's even more interesting than plain linear interpolation is just letting the network roam around the latent space, dream up whatever it wants. And this is what it looks like. While this is kind of hypnotizing and mesmerizing, for me the interesting takeaway here is that the generator has learned lots of useful things, like 3D rotation of the head and movement of the lips, eyes, how the hair grows, and so on, even though it has only been looking at individual example images. So we uploaded this video to YouTube a few weeks back, and it immediately went viral. By now there's been about 500,000 views and lots of news articles, whatever. You could watch this for hours, and I actually have another YouTube video titled 1 hour of imaginary celebrities. We can of course do the same thing with the Elsan categories. And again, let me point out that these are much more difficult cases. They contain immense amounts of variation, but so do the generated images. So many of these frames, if we were to pause the animation, look pretty plausible. Some of the categories work better than the others. For example, the 3D rotations for the cars and buses are quite amazing. For cats, the network even came up with some fake alphabet and generated captions. Conference room is nice, with the tables, chairs, lamps growing in there. We of course get funny things like horses with 2 heads, some images that simply make no sense. But there is some pretty weird and crazy stuff going on in here. In most cases, I wouldn't say that the quality is perfect or acceptable, but this is in fact the first time ever that anyone's even been able to try most of these datasets, because they haven't worked before. People have been able to successfully train the bedroom, but that's pretty much it. Okay, so while not perfect, I think at this point it's safe to check the quality and variation point. Then, as for evaluating results, you might imagine that this is kind of easy. Just look at the images, tell which one is better, but not so fast. Problem is that we're not looking at the individual images, but infinitely large collections of images. So suppose, for example, you get 2 sets of results, A and B. Which one of these is better? It's really difficult to tell because there's so much going on in here. Maybe the image quality might be slightly better in one of these. Maybe there's more variation. What about genders, equal amounts of males, females? Maybe B contains too many black people. It's really hard to tell. So for that, we invented a new distance metric that actually is able to tell exactly which one is better and by how much. Surprisingly enough, no one had invented anything remotely useful for this purpose before. So that's enough to publish a paper, but of course the more interesting question is, now that we have this stuff working, what could we do with it? There's lots and lots of really nice ideas. I'll only mention a couple. Perhaps the most obvious one is image editing, because when we have trained the generator, we know that it must contain some pretty deep knowledge about what makes a good image. So we should try to find ways to tap into that knowledge. For example, can we combine two completely different phases? And I did a quick experiment on this, where I basically take the pre-trained generator, split it into two halves, and then run the first half separately for two completely different latent vectors. And then just stitch these activation tensors together and feed this inconsistent information to the remaining layers for them to make some sense of it. And this is what it looks like. In this video, the left half will remain the same, and the right half will undergo random interpolations. So it is kind of realistic, at least as realistic as possible, given the circumstances. It's funny to see how the mouth and nose are deforming to adapt to these discrepancies. And many of these frames are such that if you were to pause, you wouldn't immediately notice that there's maybe anything wrong with that picture. Weird stuff. Another pretty obvious case is digital humans. So as a quick exercise, we took some random YouTube video with this guy talking for half an hour, and we trained the exact same kind of a network, giving individual frames from this video. This is kind of a crappy network. I trained it in 2 days, but anyways, it's generating images of the same guy, clearly. And then when we start exploring the latent space, we see the generated guy doing the same kind of stuff you see in the original video, moving their head, opening mouth, blinking their eyes, and so on. So I think this is kind of an interesting use case, and it's going to be fun to see what we'll get when we start building on top of this. Of course, one obvious case is content creation for games. Someday we might imagine generating meshes or even entire worlds with something like this. But what I'm personally most interested about is seeing what other people can come up with this stuff, because all of it is available in public. Source code, datasets, pre-trained networks, everything. So if you're interested, just pick it up and start hacking away. Thank you.
All right, thank you, Tero. I think we have time for 1 or 2 questions, but let's be quick and chat more on the break. Do we have? I think we have the first question coming up.
Hi, Tero. I think on one of some previous conferences you were displaying the kind of generation of emotions of 3D models. Do you think kind of you can progress with that kind of generation faces with emotions, and kind of how far it will go? I think it will be a huge impact for gaming industry, for animation industry, for entertainment.
Yes, most certainly. So actually that project was kind of the one of the main motivations for this one, in my mind at least, because there we didn't use GANs, and the results were barely acceptable, in my opinion. And this project was about taking it to the next level. So yes, I think using GANs or adversarial training, you can get immense improvements eventually for character animation.
Another question, maybe?
Yes, hello. Thanks for the demo. That was super amazing. I have a question. Do you think this will be able to solve the uncanny valley?
This alone won't solve it. Well, unless you think that images look perfectly realistic. There are too many kind of weird looking faces in there. But in any case, I see this as a big step forward, big piece in the puzzle. We need more pieces to solve the uncanny valley, but we are progressing towards that at an amazing speed.
All right. Maybe one more quick question before breaking. Or if not, let's thank Tero again, and we will now break for 30 minutes. The next talk will begin at 10 past sharp, so be here.
Our lives are filled with technology. It's everywhere. This technology, it enriches our lives. It makes our lives easier. It's pretty obvious to us that we can instantly connect with friends thousands of miles away, buy groceries with just a flick of a wrist, or maybe in a few years, buy that car that drives itself. A lot of technology we take for granted. Whether we notice the tech around us or not, one thing is for sure. Technology will continue to move forward, to build bridges where there are none, and create opportunities that we couldn't have even dreamed of. But how do these world-shaping innovations get started? Who starts them? Why not you? It's never been easier to start building. Now is the time. No matter what your background is, no matter where you're from, building, hacking, developing, creating is something you can do. You can make a difference. One weekend, thousands of ideas, make it happen.
All right. Welcome back from the break. I hope you got all of your extra energy from the exciting talks in the first session recharged for the second round of extremely exciting talks. The next speaker is Professor Perttu Hämäläinen from Aalto University. Perttu is the second ever Finnish professor to specialize in the technical aspects of computer graphics. And he'll be telling us about the recent advances in physically based character animation. He does incredibly thought-provoking, interesting research, I would say even groundbreaking research in this field himself, but he'll also comment on other contemporary work on that. Perttu's background is both technical and artistic in the sense that he has both a technical degree and a Master of Arts degree from the former Dyke Media Lab. And really excited to hear what you have to tell us, Perttu.
Thanks. Yeah, thanks for the kind intro and great to be here. So let's begin. I'll reset my own timer. Right. Briefly, the problem. So this talk deals with this form of reinforcement learning problem, or the kind of, we are not using reinforcement learning in a traditional sense, but the problem definition is still the same. So we have some agent that takes some actions in a world that then returns a state or observation and some reward or cost function. And the goal is to minimize the cost or maximize reward, or more accurately, the expected cumulative future reward. And in our case, the world is a physics simulation model. For example, of a humanoid that tries to get up. And why is it hard? It's because it's so high dimensional. Depending on the parameterization, it's easily hundreds of variables. Because let's say a simple humanoid model has 30 actuated degrees of freedom. They are continuous, and then you have to control them over time. So it's many times that 30 that you have to optimize. And over the years, we made some nice progress in this field, and also I presented in Syysgraph 3 times before. Here's some clips of that. And yeah, new this year. Well, we had a paper in SIGGRAPH about climbing. Then in SCA about this really fast reinforcement learning kind of thing for walking and so on, which uses tree search, but that's in for with deep learning. And then some other more human-computer interaction related stuff. I'm talking about the first SkyPlay paper on Saturday. And then there's super exciting stuff from others this year, and I'm taking some time to comment on that. First, I'll summarize the climbing results from SIGGRAPH. That was done primarily by Kuros Naderi, a PhD student of mine, then co-authored by Jose Rajamäki, another PhD student, and myself. And yeah, let's start with the teaser. So we created this kind of artificial boulderer. We demonstrated it with larger walls too, but we are focusing on the bouldering, kind of these technical climbing routes with quite few holds. And it's a kind of combination of graph search and some other methods. And yeah, before the technical details, few words about climbing as a motion planning and control problem. So in wall climbing, the goal is to get to the top hold from predefined start holds for hands. And this is interesting because it's both a kind of long horizon planning of movement sequential strategy. There's often many ways to do this. You can move in different order. Sometimes you need to do heel hooks and mantling and that sort of stuff. Jalka knows all about this. And then there's short horizon control of the individual movements. And some examples of why this strategy matters. So for example, here the climber is reaching with the other hand. And in this case, the balance is such that gravity torques the climber around. This is called the barn door effect. So the correct way would be to first, for example, move the leg. And that then keeps the balance when moving the hand. And previously, people had done one limb at a time in climbing, which is easy because if there's always 3 fixed holes, you can fully control the center of mass. But real climbing is obviously something completely different. So this is competitive climbing. So it's very complex, intricate moves. Really interesting sport from the motion synthesis point of view. And I must say, we don't yet simulate friction well enough to handle this kind of moves, but that's future work. Okay, additional motivation is this. So we have earlier created this augmented reality climbing system. It was originally a research project, but now it's also a startup, now 1 year old. And a lot of my research group works now full-time at the startup. So we think that AI agents could be useful both as game opponents or for procedural content generation in this kind of system. So what we contribute, basically prior work had focused either on some path planning work in related problems or movement control of individual moves, but this is the first time that they are both solved at the same time. How did we do it? Well, there's a simulation model, 15 bones, root is not actuated. We are simulating it with black box physics engine, and then it's a combination of previous methods that took a long time to find the combination, but in the end, it's fairly simple, so I don't spend a lot of time on it. So there's graph-based planning with A-star prune, which is a multipath planning method. Then sampling-based low-level control of individual moves. And the key to make this work is that we operate both on the full simulation state, so the body angles and velocities, angular velocities, that we call state. And then there's stances. Stances are basically the mapping of limbs to the holes, and that's basically a set of 4 indices. Here, let's say they are left hand is 2, right hand is 2, they are on that hold, right leg is 5, and left leg is not on a hold, and that's like a special index just. And we like to visualize the approach this way, so with the space of these stances in the kind of ground plane, and then the vertical axis denotes all the extra dimensions from the body rotations and stuff, meaning that one stance maps to multiple poses and states. And then in this stance graph, we can then perform path planning and try to move between the stances in the state space using movement optimization. And if this fails sometimes, here shown in red, so then we dynamically adjust the edge costs and replan. And in the end, this process grows a tree in the state space. And individual movements are synthesized by minimizing a cost function with these components. And this is what the result looks like. I'll talk more about the motion optimization in the next paper. Future work we are currently working on, or our partner is working on the finger and hold details, improving that. In this work, it's only a kind of ball and socket joint that once the carrot gets the hand there, it will stay. And then we are basically improving speed and quality, getting rid of all kind of hand-tuned heuristics by using machine learning to let the system figure these things out itself. Which brings me to the second paper. So I'm really happy about this work by Jose Rajamäki and myself. It's It was presented at Symposium on Computer Animation, co-located with SIGGRAPH. And so this is about also the problem of adding machine learning to this sampling-based movement synthesis. So basically, we can learn really fast this kind of movement skills like locomotion with different character types and also dodging projectiles and stuff. So it's fairly robust. And now, what is this sampling-based control? Basically, in all our work on a high level, it's this. So we sample controls, let's say, for example, joint torques from some PDF, so probability density function. Then we forward simulate and evaluate the controls. And in this case, when the character moves, its root will draw these trajectories. So these visualize the forward simulation. And then we evaluate those simulated trajectories. And if this is an online case, so that we are doing this on the fly, then we use the best trajectory to advance the so-called master simulation, and then we run the process again. But the key here is the fourth step, so how to evolve the PDF so that it produces better samples of controls for the next iteration. And previously, so we haven't used learning here, so basically there's one iteration per animation frame. We used the best trajectories of previous frame somehow as the PDF. So we basically assume a pretty strong spatiotemporal coherence so that similar controls will also work in the next time instance. And then we forget everything else. And for example, in SIGGRAPH 2015, we proposed this factorized PDF formulation of the trajectory distribution, which then allowed us to use belief propagation. Basically, first sample some segments and then run pass messages forward and backward, second forward pass, then backward to kind of produce this weighted empirical distribution that then forms the prior for the next frame. And this worked fairly well, so we could do stuff like juggling while interactively kind of teasing the character with the mouse. And it improvises these things. So those emerge. We have just said that it should keep the ball on top of its head. And but the movement is fairly noisy. And the worst thing was locomotion. Basically, stable gait does not emerge. Okay, it's cool that you can control it in real time, but since it's improvising every step from scratch without any memory of previous steps, it's kind of, zombie was the best we could do with that. What was kind of new that nobody had done before was this kind of robustness to obstacles. So we can make it climb over stuff. Yeah. Let's see one more. Yeah. Okay. So movement is not perfect, and also we had to quite carefully formulate some priors for the sampling to make it work with limited sampling budget in real time. So this year, we found out that, okay, we can do much more simple algorithm and simplify the hell out of it and still get better quality if it just adds some deep learning. And here's basically this new simplified controller without learning, so it works even worse. Very, very shaky. But then when we turn the learning on, it starts to stabilize basically within seconds. So this is captured from one learning session. And that's something like 10 seconds to 15 seconds of experience, which means here about 30 seconds of CPU time. It has already found a gate, and then you can reduce the sampling budget for real-time operation. Okay, just briefly how it works. Okay, there's very simple forward tree search. Let's assume we are controlling something vertically, And we start from here, and then at each time step we sample some controls like vertical accelerations. There's some goal point and there's some obstacle. Well, if you just randomly sample trajectories, it's something like that. But of course, it makes sense to apply some early termination. And in this case, we just have a threshold that there's some best trajectory so far, and then if some trajectory has cost significantly higher, just some threshold multiplier, then we terminate it and we assign the simulation budget again to some better trajectories by forking them. So there's always a same number of kind of these parallel explorers of the future going on. And then for the next frame, we select the best trajectory as the control, and then the process repeats from there. And the key idea is that these trajectories have different roles. So basically, we are combining multiple information sources. Some trajectories explore without any prior info, just randomly. Then there's one initial guess is the best trajectory of the previous iteration. So again, assuming spatial-temporal coherence. Then there's some trajectories informed by other previous iteration trajectories, and then there's machine learning trajectories. So basically there's policy. Policy is a function that maps current state to some action. And we have two types of machine learners doing that. And these policies are trained in supervised manner with the selected control. So the best control found in each iteration becomes a training sample. And then we gradually forget very old samples because we have, assuming that we have already learned a distribution of better ones. So it's super simple. And interestingly, these components then kind of augment each other. For example, the previous iteration trajectories are useful when the system has not learned yet or is exploring new things. But then when we add these other components, we always get lower cost. So the black one is with only the previous iteration trajectory, so kind of the baseline. Then we add nearest neighbor learning, so we just remember all the best controls and use them again based on the state distance. And then this is without the nearest neighbors, but with a neural net that learns the policy. And this blue trajectory is with both learners turned on. And yeah, there's some. So basically, there's not that big a difference, but the nearest neighbor only is kind of a bit more shaky. And yeah, like I said, the strength is that it runs fast. With simple models, the learning too works in real time, and it's fairly robust. And let's see, a few more characters. That wasn't that natural. We should work on that, but still. And one thing that has been really a problem is this sudden changes of target direction. So on the right is the kind of guy who has 5 minutes more experience. This is the kind of newborn that is quite confused. Then we tried some other characters. So basically, you can give it any kind of physics simulation character, and it seems to find fairly good gates. And then they improvise interesting things, like on the right. Now it uses the momentum of the ball to get back up. Okay, so to our knowledge, no previous system learned a stable gate so fast, so it's used to take hours or even days. And with this system, the cost function designer gets immediate feedback because the tree search thing kind of skips the initial learning. So if you compare to pure reinforcement learning, there's often an initial period where it just fails all the time and falls. But now you can kind of immediately see whether the cost function is in the right ballpark. Some lessons learned. So simple tree search plus learning is very useful. It's actually what also AlphaGo Zero uses, pretty similar system now. And you don't need a critic network. Those working on reinforcement learning know that the whole Bellman recursion and critic networks, there's a lot of problems with that. Okay, now I have like 7 minutes left, and I'd like to take this time, instead of going into more detail about our own work, instead reflect on some other breakthroughs. So originally I was going to talk more in depth about our own work, but then something happened a week ago. So this happened. You've probably seen this. And this is awesome. It's first time we see these things in a real humanoid robot. There's been some like really miniature robots that have done backflips, but nothing like real size and with this agility. It's just, yeah, mind-blowing. And I mean, a couple of years back, and still the kind of robot soccer competitions are, this is how it is. So that backflip and parkour, that's really a breakthrough. And I think the Atlas backflip kind of crystallized that this is really a special year, because earlier already this year, at the same time as we were in SyGraph, basically, OpenAI published proximal policy optimization. It's a reinforcement learning method that just provides some really cool results, beating the competition. And if you don't know OpenAI, so last year they released this OpenAI Gym, which is basically a set of Python benchmarks, really easy to use for these classic control problems. And OpenAI is backed by Elon Musk, and probably so they try to crowdsource the algorithm development with this. And this is literally all that you need, for example, in Python to get started. So this creates a standard kind of benchmark, runs it, and then so you sample some actions, and then you get some observations, rewards, and stuff back. It's in this kind of episode, so that you run the system until the character falls or something like that. And then if you want to start doing reinforcement learning, you just figure some way to sample the actions and then feed these observations to the algorithm like PPO, and OpenAI provides open source kind of standard implementations. And this is maybe the hardest benchmark there in OpenAI, the RoboSchool. So previously, before PPO, no reinforcement learning algorithm could robustly solve this. And mind you, this kind of getting up, for example, was the main contribution in our first SyGraph paper only 3 years ago. But that was using the forward chairs, and this is using no such forward chairs, which takes a lot of CPU. So this is just a trained neural net policy, which is you can basically run on a decent laptop. Let's say probably with this gaming laptop, you could run like 100 of these characters in real time. It's fairly simple network in the end, and yeah. Why is it impressive? It's because this continuous reinforcement learning kind of, well, I don't really have time to go into that, but the key is the Bellman backup there. So basically, you try to estimate a gradient of the neural net parameters, the theta, with regards to value, which is this recursively defined thing. So there's the instantaneous reward, and then the expectation of the rewards in the future, given that you follow the policy. And that's super hard to kind of compute correctly, and it limits the ways you can explore and so on. And third thing, if you want to get started with PPO, for example, it's now available in Unity, because this year Unity finally released the 2017 version. .1 supports a fairly new .NET, which also allows easy integration of TensorFlow. And now Unity has released this kind of beta TensorFlow integration with these demos and tools that you can start tweaking from. So here's, for example, PPO, learning to balance the ball. So to summarize, I truly think we are at the culmination point of some 30 years of progress. So let's review the history. So 88, Wittgenstein has published the space-time optimization kind of really seminal paper where the 2D Luxo lamp could basically jump to goals and so on. And then in the 90s, there was a lot of work on genetic algorithms, early reinforcement learning with simple characters. 2000s, some limited optimization-based control of 3D humanoids. And 2010 and onwards, the forward simulation and search really became feasible. So physics simulators were mature enough, and there was enough CPU to do that. And that's where I jumped in also. Tassa's 2012 paper is another very relevant one. And robotics started using kind of simulation. And then happened the ImageNet, the Hinton and others paper, TensorFlow 2 years ago, last year OpenAI Gym, and about half a year later or something, first 3D humanoid successes, still very slowly learning. And now this year it's Atlas Parkour, PPO, Unity machine learning, some really cool competitive self-play like AlphaGo 0. And my take-home message is it's never been as easy to get started and start developing some new applications for this or some new algorithms. And I kind of predict a major gold rush, an era of innovation. For example, in AI game control, game mechanics, game testing. If you have an idea, start on it now. Next year, somebody has done it. And yeah, I think that's my talk.
Thank you, Perttu. I think in the interest of time, we have to defer questions until the after party, unfortunately. But thank you, Perttu, for this overview. He's a modest man. He did not underline the fact that it was OpenAI and the luminaries in there who took hours or days to learn to walk in the same way they learn in seconds. So that's, I think you're underselling, man. And so these problems are incredibly hard. But it is now time to move on to the final talk in our session. The talk is going to be given by Professor Tamy Boubekeur from Paris, the University Telecom Paris Tech. Tamy is undeniably one of the most prolific researchers in computer graphics in Europe, in particular for his age, but by even disregarding his age. His work is incredibly broad, from rendering to modeling, and all kinds of really interesting things. He's also not just an academic. I didn't mean to say that. He also has strong ties to the industry. He, on the side of his professorship, he's the CTO, or chief scientist, of Algorithmic. That's a French company who make software called Substance Painter and Substance Designer, tools for modeling materials that I'm sure a lot of you in the audience are familiar with. And tonight, Tamy is going to tell us about his latest work on modeling with some connections to the things that we saw in Vin's talk earlier for Umbra. So, Tamy, really great to have you.
Thank you very much, Jaakko. Thanks for the kind words and thanks for the invitation. I'm very happy to be here. My talk will be about one kind of object that we are developing with my group for a few years now that we call proxies. And it's not a technical talk. I will try to just give an overview of a few examples of what that kind of object can bring to computer graphics applications. But before, let me present myself. I used to work at INRIA in France. I did my PhD there. At the same time, I was also working at the University of British Columbia in the Imager group. Back then, I was working mostly on data structures. I've always been really interested by trees and how trees can help graphics application if you design them well. So I worked a lot on that. And maybe the other side of my work back then was to be able to manage large amounts of data. We saw a talk earlier about billions of polygons, and this has been a challenge for years to make graphics application handling so much data. And so much data is so few compared to what you actually need to get realistic. So that's a long-term goal. Then I moved to TU Berlin as a research associate over there, and I started to expand my activities mostly around computer vision and to some extent machine learning techniques. And then I joined Paris, founded the computer graphics group over there, and keep expanding the topics we are studying. I like the idea that my group is working on both modeling and rendering because there is a lot of things going on at the interaction of both. And most of our research is fed by this double goal, of course with some computer vision and some machine learning techniques. As Jaakko mentioned, I also became the chief scientist at Allegorithmic in the meantime. Just a word about Allegorithmic, if you don't know this company. It's a company that developed a technology called Substance to model materials. We have a bunch of technologies actually within Substance to either create new materials from purely procedural behaviors to scan-based data. And we have also a bunch of technologies to actually apply them. So probably that Allegorithmic became really famous when Substance Painter was released, which is kind of a Photoshop for 3D material, so that you can actually paint on surfaces and you have directly the response that the material would give once rendered instead of painting layers in Photoshop and then importing them. But Allegorithmic is going beyond that. So basically the company is expanding quite a lot these days around first trying to model all materials in the world and then interfacing to new industries like design and architectures. I'm spending just a few seconds here because, of course, we hire a lot. So if some of you look for some jobs regarding rendering, material capture, computer vision, even machine learning, we have plenty of opportunities all around the world, actually. So do not hesitate to contact us. On the website, there are plenty of offers. But today I will go back to the academic world. Most of the work I will present is the result of the group that I have the pleasure to lead in Paris. This is the current group, and it's a manageable size compared to other groups. The main topics that we are studying is, as I said before, modeling and rendering, and to some extent, those two topics actually fit fairly well to computer vision as well. So there are a bunch of computer vision problems that you can address with graphics techniques, and we try to do that as much as we can. Today I'm going to talk specifically about a line of work around shape analysis. So we have our specific take on what is shape analysis in my group. Okay, we are computer scientists first. We use a lot of mathematics, but we are really interested in machines and the way they compute. And we try to match two kinds of objects. On one side, data models, which are prominent these days, in particular in the era of software 2.0, as some people say, but also computational models. There are many ways to actually compute the same things, and deciding which one to actually deploy might be driven by some constraint, like the one I like the most, which is speed and scalability. So how fast can you go and how big can you go with algorithms that recognize shape, reconstruct them, filter, or render pictures. And from time to time, it's also a good idea to design your algorithm so that you keep the user in the loop, and the user can actually interact with the most fundamental pieces of your process or your framework. So this is the way we develop shape analysis in the group. And I will give you a few examples of what this can bring. Probably some of you are familiar with scanners, when you start to capture the real world and create point clouds, and then from the point clouds you reconstruct meshes, then you simplify them and so on. most of those operations are processing stage, which means that the input of this stage is a 3D shape, and the output is also a 3D shape. Most of the digital geometry processing community, for instance, has been working for the last 10 or 15 years over those basic operators, which are simplification, filtering, subdivision. And if you go back in the 70s, there were already questions around how do I refine my mesh so that it is smooth or look like a smooth surface, or how do I decimate it so that I keep most of it. So this is geometry processing. Now, geometry analysis is a little bit different. From the analysis of your 3D shape, you extract parameters. And those parameters are application dependent, and for instance, they can feed processing stages, but they can also feed editing tools, like freeform modeling tools. They can feed AI recognition system. You can do a lot of stuff with shape analysis as soon as you design properly the form of your parameter set with respect to the application you target. Let me give you a more precise example of what we used to do before. So we had for a few years with my colleagues at TU Berlin this aim of making a 3D Google. Like, we would like to have a search engine where you can query large databases of 3D shapes, the same way you query actually a search engine today. When you query a search engine today, you don't submit to Google a web page and expect to get similar web page in exchange. You submit a very short description, very compact description of what you look for, and the engine brings you a list of very complex web pages. Keywords, that's your queries. So the key question back then was, if I have a search engine where I can search, when I want to search easily 3D shapes, what kind of queries can I formulate to the computer so that it's short, it can be done by anyone. Obviously, I draw this little drawing, and it's fast enough so that you actually can refine your queries over time. For us, clearly, drawings, simple binary drawings, not made by artists, but by your kids, for instance, should be the ideal input to such an engine. And ideally, the engine would be so fast and so efficient that you could assemble entire 3D scenes with just a few drawings and then locating the different objects. So we kind of succeeded after 4 years almost of research to get such an engine running. So what you see here is a live capture of the engine back then. You draw a few things, a few lines, and from the lines you recover a list of 3D objects in real time. And the real-time aspect is very important because not only you draw what you look for, but also you adapt your drawing to what the engine is able to actually provide. Sometimes you realize while you're drawing that some behavior in the drawing, some type of line help actually refining your search better. This was back then, I think it's still almost, deep learning did a lot of stuff since, but it was back then state of the art in visual search from line drawings. And it all relies on one kind of tool, statistical analysis. So I'm not going to go too deep, but I will give you a few details about how that kind of things work. Indeed, a part of your eyes, a 3D mesh and a 2D white and black drawing have nothing in common, pretty much. That's in your eye that those two objects become actually similar. So we bootstrap the system by extracting a collection of significant views of our shapes. So we have a statistical model that tells us basically how to sample views and then decide from which point of view an object is likely to be drawn. From those point of views, we generate something which is as close as possible to what are drawings, which is line renderings. Line rendering is actually a field in computer graphics. And a lot of people have been working on trying to find algorithms that extract the most relevant 3D lines, or even 2D lines, from a 3D shape. So this is the basic initial conversion that we performed, and from that we deployed what's called the back-of-feature engine. It's an architecture for learning a dictionary of visual words that describe a given object, and which has several good properties. The one we described specifically, we developed specifically, was based on a new kind of descriptors called Gabor descriptors. Those descriptors are basically here to detect the direction of dominant lines in some region of the image and their magnitude, their scale. No need to go too deep into how those descriptors are made. Basically, it's a statistical description that first learns a visual dictionary from a collection of shape and then project each shape as a set of occurrences in this dictionary. And that's your description. That's what you're going to search for. This has plenty of good property. It scales fairly well to large amounts of data. It's naturally translation invariant, so you can draw wherever you want on your screen. You can easily make it rotation invariant or scale invariant, so you can basically play a little bit with the orientation of your drawings. And thanks to the Gabor bank filters, we were also able to handle some form of deformations in the drawing, because a part of the true artists that probably are here, most people just cannot draw. You cannot like draw two lines which are perfectly parallel. Most people cannot do that. So that's a statistical analysis that brought us to a search engine to find very quickly 3D shapes from simple line drawings. And we expanded that kind of approach to other kind of problems back then. In 2014, for instance, we developed the SimSelect system, this system that you see here on the demos, where basically the idea was to help the user with something that you probably do all the time, which is selecting stuff. When you have a 3D tool, like you spend a lot of time selecting stuff before defining what you're going to do on the stuff you selected. So we thought that this is a very painful task, and there is one way to actually limit a little bit the amount of work you have to put in when you select stuff on the 3D shape, which is exploit the self-similarity of a shape so that you can expand your selection to anything that looks like what you just selected. So this is the system you're seeing here. You just select one region, and then you can automatically expand it by, again, a form of statistical analysis. Here, it's not reasonable to think that you can expand any form of selection to any kind of shape in real time. So we use the fact that there is a little bit of semantic in the way you select things, which means that basically you're going to click on components, you're going to cut parts, you're going to brush regions, and each of those different interactions brought us a way to actually bootstrap very specific learning algorithm to detect specific kind of similarities when we were looking for potential selection. Again, these are statistics. The way we actually put in correspondence the different object components are based on some form of histogram, of some spectral analysis projection of the objects, or sometimes even descriptors that would account entire components and project some gradient information into some common basis. I'm not going into detail because what you have to understand is that those little drawings here are the core objects behind the form of analysis that is performed here. And they are very similar somehow to the one that were used previously for the line drawing search engine. And this brings interesting questions, like most of those objects are for indirect use only. There's no way I can create a 3D Studio Max plugin where I would expose those objects to users. And that was a problem for us because there were many shape analysis applications where we wanted the user to actually interact with the set of parameters that we would extract. So no direct use of what was learned with that kind of methods, hard to interface with humans. And actually there is a third problem, which is that sometimes from what you learned from the analysis, you'd like to recover actually a shape. Maybe not exactly the original shape you had, but at least some information that helps reconstructing the geometry of the shape. It's very hard to actually reconstruct a shape from that kind of statistical description. Same goes with images, by the way, because that kind of methods are also used in image processing and image analysis. So the question we asked ourselves was, can we extract parameters which are 3D objects themselves? And there are actually a collection of applications where the shape analysis process is supposed to end up with simpler objects, objects that describe roughly the input shape, and which are used in substitution to this shape. And here comes what I call shape proxies. So these progressively come to a common name among practitioners. Proxies are basically a form of spatial analysis of 3D shapes. It's essentially grounded on a well-known process called surface simplification. Surface simplification is a way to reduce the resolution of a 3D surface while maintaining as much as possible its overall geometry. This is used in many applications, and you saw earlier an example of level of detail algorithm that tried to do surface simplification at very large scale. So there is a full record of previous work on this topic that probably started in the early 90s. And the key idea is to go further. The key idea is to push that kind of methods, or maybe even design new methods, to extreme level of approximation, so that in the very end, you keep only very few numbers to describe your shapes. And these start to be shape analysis when you do that. So we want to use them as substitutes for graphics and vision algorithms. Ideally, some of them might also be useful to users directly as high-level structures. I'm pretty sure that when you see this shape on the right, you think about rigging, skeletons, and the way you do maybe animation in your applications. This is one potential application of those. And to exemplify that, I will take two examples of shape proxies that we developed over the last few years. The sphere meshes that you see here on the right, and what we presented this summer at SIGGRAPH, the bounding proxies. And you'll see that they are complementary and cover quite a set of potential applications. Let me start with the example of sphere meshes. So if you look at this shape, you may wonder, how can I approximate it with 1,000 primitive, for instance? That's what you get with a traditional high-quality surface simplification algorithm. I would say that 1,000 primitives is probably a low budget, so this is a very good result, actually, to approximate this shape. Now, if we apply what I just said, if we push the principle a little bit further and try to get 35 primitives, well, the algorithm spectacularly failed, and some entire volume collapsed to flat regions. Obviously, with 35 polygons, I just cannot recover the original shape. One of the reasons is that the surface representation here is a simple surface mesh, and at some point, when you have a very low number of values, it costs a lot to actually delimit a volume with polygons. And our observation was that when you go very coarse, if I summarize, somehow your samples need to encode the volume itself instead of just being located on the surface. And there is a trivial solution for that, which is that your samples may actually be simple spheres. So what you look at here is a structure that we call sphere meshes. It's just a mesh, just the kind of mesh you manipulate every day, only it's 4-dimensional. So you have for each vertex a 3D position and an extra parameter, which is the radius of a local sphere that is supposed to locally capture the volume of the shape. And you can see that with 35 primitives here, the shape reproduction is much better, and we can think about a bunch of applications in rendering and modeling based on that. I'll try to convince you with applications later. So an observation first. When you start to go volumetric like that, you might not want to go volumetric all the time. For instance, if I give you this input orange shape, and I give you a budget of 8 spheres, 8 samples, well, it turns out that the structure of the mesh is actually a homotopy equivalent to the original object. Now, what you see on the right here is the actual geometry of the proxy. And here is the first insight. When you consider a polygon mesh made of triangle, you can consider that the geometry defined by a triangle is actually a point interpolation process in the barycentric space of a triangle. If you apply the same principle to one dimension up, like spheres, you can consider the geometry of our sphere mesh here is a sphere interpolation, a barycentric sphere interpolation over the simplices of your complex. And that's what we do. So basically, it allows to, for instance, change the topology of the structure. Here with just 4 spheres, the algorithm automatically finds that a 2D sheet made of 2 polygons is enough to actually cover those 4 spheres. And if you just give 2 spheres as your budget, you end up with a single segment. What's interesting also is that, I will explain the algorithm later, but probably that if I give you an application, an interactive application, give you the input shape, and then ask you to locate spheres with this principle by hand on the surface, that's probably what you would do. What I'm going to present now is not data-driven. It's just an optimization process based on a simple metric. OK, so this is the core definition of what is a sphere mesh. A sphere mesh is basically a set of spheres indexed by edges and faces, and the geometry of the resulting proxy is defined by the linear interpolation of those primitives over the edges and triangles. Now, let's go a little bit deeper and focus on the sphere, this one sphere that I might use to actually represent millions of polygons in one region of the shape. The first thing that we came up with to do this was to actually design a specific metric to help localizing efficiently those spheres around the shape. One thing we developed is, in particular, a measure of the distance between a sphere and an oriented plane. You will understand in a second why we do that, but basically at some point when we have a set of sphere, it's very important for us to be able to measure how close the sphere is actually to the surrounding geometry. And for us, the input is a triangle mesh. So the surrounding geometry is basically a set of planes. Now, we make sure that this distance measure is actually signed. Basically, it can account for the orientation of the local plane so that you don't fit spheres outside of the shape. And interestingly, we can easily then detect that some spheres are located in some convex regions or remove any spheres that might actually fill up concave regions, because you definitely don't want to fit to fit a sphere outside your object. Now, the square distance, the square of this distance is actually an interesting object, because it actually takes the form of a scalar field in space, which is actually a quadric. It's a quadric in the four-dimensional space defined by the spheres, the potential spheres that you might use to fit your geometry. And what's interesting is that when you have several planes to fit, actually the sum of those quadrics in 4 dimensions, is also a quadric. So you start to see the algorithm appearing here. For entire regions of the shape, I can actually compute those different quadrics, sum them up, and optimize for just the resulting sum, a single quadric for a single sphere, to actually locate automatically the sphere at the optimal position. Now let's lay down this to an entire algorithm. It's actually a simple graph reduction, very popular in surface simplification algorithm. You're going to start with all the edges of your surface mesh, compute the spherical quadric for each of them, sum them up per edge, and then create tokens that you're going to put in a priority queue. This priority queue has then tokens with the edges, the resulting optimal sphere corresponding to one edge of your mesh, and the cost that tells us basically how bad or how good the approximation of the shape will get when I replace an edge by the resulting optimized sphere. Now, this is a priority queue, so I'm going to sort them by the cost and take the best one, which has the lowest cost, remove it, collapse the edge, compute the optimal sphere, and update the set of edges in the surrounding. Now, if I iterate this principle, you quickly get that kind of structure, where progressively you will replace surfacic regions with volumetric regions, which are those spheres interpolated over space. That's it for the description of the algorithm. There are many technical details to account for curvature and other stuff, but here are a few examples. On the left, you can see that the algorithm has this nice, graceful degradation property, which means that if your budget is not high enough, for instance, to reproduce a complex topology, an object with a complex genus, for instance, the simplification or the approximation algorithm will still give you something which is geometrically meaningful. On the right, it's even more interesting. You see that when you just give 12 as the budget for fitting this fish model, you get something that reflects the symmetry of the shape, while symmetry is not explicitly modeled in this particular metric. And probably that, again, if I give you a simple tool, like ZBrush, for instance, and if I ask you to create a Z-sphere model where you would locate the spheres, probably that if I constrain you to 12 spheres, that's the kind of structure you would end up with. Interestingly enough, those spheres are also naturally located into joints when you have like natural characters with arms and legs. And compared to skeletons, for instance, keep in mind that not only you have edges that can link your spheres, but you can also have polygons that defines flat surfaces. Can we go harder? Back in 2008, I used to work on capture, like large amount of data and so on. And one of the things we worked on with my colleagues from UBC was pure markerless performance capture. So can you reconstruct an animated surface just from a few observations made by the few cameras at high speed without any marker on the deformed geometry? That worked fairly well for garments here, and surprisingly, the resulting data is not that useful, I would say, because it's a frozen sequence, a raw mesh for each time frame. We made sure that the mesh has a topology which is compatible from frame to frame, so the connectivity is exactly the same, but you can just basically replay it. This has applications, of course, but obviously this would have way more application if you could actually structure this data with a control structure, a rigging, an automatic rigging that would fit the data. So that's a direction we took much later, actually last year, which was extending the sphere mesh model to animated data. And so that's what you see here on the left. We choose a particular level of detail and computed an animated sphere mesh over it. On the right, the optimization not only optimized for the trajectory of the spheres, but also for their radius. This is a variation of the method. And interestingly, when you handle animated data, all of a sudden, there is not a single local geometry that you have to fit. This is an entire sequence of geometric situations that you have to fit with a single sphere. So the one edge I was collapsing before, this time the sphere that would result from this collapse has to account for the geometry of the local patch it's simplifying all over the sequences. And so at one time frame, you have, again, one quadratic matrix, as I had before, but I have many more, as many actually as there are time frames in my capture. Surprisingly, not surprisingly, but interestingly, you can actually assemble all of those local quadrics, small quadrics, local in time, into a single big one. So there is one much higher dimensional quadric that is actually composed by all the small ones. And we can again optimize for it and get the ideal sphere, at least in the least square sense, that fit the sequence locally. So that basically fit the geometry of this surrounding of the one edge over time. Okay, so now that I described how to compute the proxy, how can we use it for doing stuff with it? So one of the things we really like in the group is freeform modeling. We like to design applications where you can interact with the shape, move them, deform them, and so on. From our perspective, that kind of sphere mesh model is a good candidate to actually control the original shape because it's multi-resolution. Because if you get 100,000 vertices in your input, you can generate 100,000 level of details of this input in less than 1 second, which means that you can really easily load large models and navigate level of details in the control structure. And the key idea is that you can actually rig a mesh with its sphere mesh, which means that you're going to use the sphere mesh as the interaction interface and transfer the deformation of the sphere mesh onto the original high-resolution object that you might use in your final application. So compared to other methods, there is no need to manually design a skeleton, for instance. There is no need to paint vertex weights. This is all entirely automatically computed. And the interaction is actually fairly simple. I don't know if this can go fully professional, but for sure for the everyday user, just loading a mesh and the next second being able to actually deform it smoothly with kind of meaningful interactors kind of makes sense for us. Other application includes, of course, everything that relates to physics. Not everything, but some things that relates to physics, like collision detection over animated sequences. This is actually quite costly because if you want to do a collision detection over an animated object, there is not that much choice. The best you can do is actually compute a BVH and update the BVH over time. Here we have a much simpler object that provides an approximation of the collisions over time, which is again computed at load time very quickly. You can go even further. Let's consider this much more complex performance capture sequence. Again, it's an animated mesh, pretty dense here. We can actually extract the motion attached to this object in the form of an animated sphere mesh. And by doing so, we're going to link one frame, just one mesh of this sequence, to the sphere mesh by computing automatically a skin map. This skin map is optimized to account for geometry and motion during this sequence. And in the end, we can reconstruct the entire sequence by just keeping one static mesh and recording the animated sphere mesh that we optimized before. So this has compression interest, but also interaction interest. You can then start to edit the motion through the sphere mesh instead of trying to edit the animated surface. The sphere mesh model was quite successful. Actually, a bunch of other groups started to use it for various purposes. It has still limitations, and one of them is probably that some proxies, to be really useful, they need to have a bunch of constraints that make sure that they are conservatives. And that's the objective of what we developed recently called bounding proxies. So bounding proxies are built upon a framework called mathematical morphology that we started to develop actually in 2014. We are definitely not behind mathematical morphology. It's a well-known framework in image processing, but we started to make it more compliant to computer graphics application. What you see here are simple morphological filters. There is no user control beyond just one parameter in those two videos, where a morphological operator is applied on the shape, and you can see two interesting things. On the left, there is a filtering operator that not only removes small-scale, high-frequency content, but actually removes entire components smoothly. But most interestingly, any component which is not removed remains full res with all the signal content. On the right, you can see a different behavior. Here, the topology of the shape is simplified, and any piece of geometry that do not participate to this topological simplification remains still. It's untouched. And all of that was performed by just implementing two operators in the mathematical morphological framework that we proposed back then. Let me go deeper on one of them. So let's take this input point cloud. It can be a mesh as well. It doesn't really matter. So this is what we call a dilation of the shape. This is an erosion of the shape. And A slightly more advanced operator is called the closing. This closing has several pretty nice properties when it comes to computing proxies. It's actually very tied to the input. It's coarser because it has a tendency to fill up concavities and maintain convexities, but as soon as you fill up the concavities near a convexity, all of a sudden the feature disappears. It's a naturally abstract topology. So the coarser you get, the more holes you will fill in your volume, and this comes for free. You don't have to actually detect them or model them explicitly. We observed that back in 2014, and we started to work on a proxy model based on this framework. But let me explain you what is mathematical morphology. Let's take an input shape, whatever the representation. The idea of morphology is basically to use two complementary operators to alter it. One is called the Minkowski sum. The other one is called the Minkowski subtraction. And the core idea is that you're going to consider a structuring element, a simple shape that you will use to analyze the input geometry. Depending on this shape, you might extract different kinds of alterations. And actually, the design of this shape is an entire field of research. Let's take the simplest one, a simple sphere. When you do the Minkowski sum of the input shape with the simple sphere, the core idea is that you basically, for any point in the input, add the volume of the structuring element anywhere, which means that you're going to sum up, that's the Minkowski sum idea, you're going to sum up a sphere onto any possible point on the surface of your object. For the Minkowski subtraction, this is the exact opposite. You remove volumes based on the structuring element, and you basically carve your geometry. When this framework gets really interesting is when you start to chain operators. Right? These two operators are very simple. I just have to specify a structuring element and an input, and that's it. And I can apply the operator. When you start to chain them, you start to have behaviors which are highly interesting for our purpose. In particular, what you see on the top here, which is starting with a dilation and then eroding the dilation, yields what we call a closing. And this closing has actually many of the properties we want for proxies. So a bounding proxy, in our case, will be a polygon mesh that acts as a lightweight geometric substitute for all the applications that require to have actually a conservative approximant. So those applications include freeform modeling, cage-based deformation, where you use a simple cage around your shape to deform it smoothly. Physical simulation, when you want to diminish by order of magnitude simulation time by simplifying the object used for simulation, but not the one used for rendering, of course. You want high-quality images. Level of details, when you want to reduce the complexity of your geometry for distance viewing or for distance visibility queries, occlusion queries, and actually many others. So what are the key properties of a proxy in this case? Well, basically, it has to be bounding, which means that the proxy should contain the input. It has to be coarse, because most of the interest of using proxies is to diminish the computational needs when you run algorithm on the proxy instead of the original shape. So the coarser it gets, the better is the benefit for you. It has to be tight. A bounding box is not a good proxy for most of those applications. And ideally, we'd like the proxy to be as close as possible to the object, but not crossing it, completely containing it. And if possible, it should be geometry adaptive. If you have like some features that exist at a certain scale, they should reflect in the proxy, as well as user adaptive. If you have a designer that knows exactly where he needs details and where he can afford coarseness, well, it makes sense to let him control the behavior of the system. So our solution basically fit up all those criteria by construction and in a pretty scalable way. I'm just giving you here the main stage of the algorithm that generates those proxies. The key idea is to first move to a space where morphology is easier, which is volume representations, and in particular voxels. So starting from the input mesh, we're going to use a state-of-the-art conservative voxelizer to get a voxelized version of our object. Then we developed a specific closing operator, which is designed to run in parallel on the GPU at very fine scale, and actually in real time on modern GPU, even at high resolution. This closing yields shape variations at different scales, which might actually be controlled by the user using a simple brush. So the user, as you saw previously in the video, can just paint the scale at which the approximation should appear, and in real time, the algorithm updates that. In the very end, you need to export that in a mesh format, so we have a feature adaptive mesher that still preserves locally the bounding condition that we have been working so hard to maintain. Here is an example for designing the cages I was mentioning before. So basically, the user has an interactive feedback through the morphological closing on the voxelization, and the brush is actually controlling a scalar field that defines at which resolution the geometry should be simplified locally. There are actually a bunch of fields that we use here, in particular an orientation field to also align the geometry locally to some user constraints for the final meshing stage. Okay, so these cages have several applications. I showed a few examples with deformation. Let me show you and discuss a little bit more simulation. Here we have deformable models which are displayed at full resolution on the right, but for which the animation was computed on the bounding proxy. The bounding proxy actually undergoes here a deformation through a simulation, and this deformation is transferred to the original high-resolution object using what cage coordinates, essentially. This yields a 100x speed up in this case. Here is an even more interesting case. You might think that simplification algorithms are enough, but in this case, for instance, when you just simplify the object and run the simulation onto the simplified model, obviously you get that kind of pass-through artifact when you play with very thin geometry like clothes. In our case, the bounding proxy is actually conservative, so there is never any pass-through artifact in that case, and it's much faster, about 22 times in this case. Even for applications which are not so critical regarding conservativity. Let's take this complex mesh made of millions of triangles and apply a state-of-the-art simplification algorithm. Well, the simplification algorithm has no real idea of the volume represented by this collection of small objects and has a tendency to actually degrade the overall density of the geometry. With morphology, actually, for the same budget, 1,000 triangles, the morphological framework acts as a geometry and topology regularizer that helps better laying out the simplification step. So that's the kind of level of detail you get through morphology. You can go even further. Let's go back to animated data. They are the most complicated data you have to process these days. And so when you have these animations, one thing you can do with your proxy is actually to reverse engineer the input motion into the motion of a simple cage, and then reconstruct the full sequence by applying the deformation learned on the cage onto one single mesh of the original input. You see here examples where there is a specific optimization we designed here that was actually the core contribution of this paper. I'm not going to talk about that, it's a bit technical, but the one need of this optimization was to have a good cage to start with, and bounding proxies can act as good cages. Okay, so let me summarize a little bit those different points. Shape proxies, they are like lightweight substitutes to your complex model into your 3D softwares. They can be used to substitute the geometry for algorithms, to speed them up. They can also be used as high-level controllers for users so that they can interact with the shape with a lower number of degrees of freedom. What's interesting is when you can actually control all of those proxies. Control their resolution, control how coarse they get, control also the way they are generating accounting for features and other details which are important on the shape. I showed you two examples, sphere meshes and morphological bounding proxies. They are pretty complementary, and there are actually, in our work, many other kinds of proxies that we have been developing over the last few years. You can also see them as some form of superstructure for raw data. You can use that kind of methods on shapes that you would model with 3ds Max or ZBrush, but they really get interesting when you start to process scan data. So basically, when the data just comes as a list of points or a list of random polygons on a surface, and you want to recover some structure over it. As you saw also, it's very often all about metrics. If you design a metric that properly captures the approximation power of your proxy, you can then use it to generate the proxy, locally refine it, and decide whether you're going to stop generating more elements in your proxy or keep going. The design of metrics for shape approximation is actually, from a scientific point of view, the most interesting aspect of those projects. And finally, as a side note, it turns out that mathematical morphology that we used in two projects here is fairly unexplored in computer graphics, and it has a behavior very different from other geometric frameworks, very popular in graphics, like spectral analysis, for instance. And if some of you are going toward graphics research, I encourage you to look into that kind of morphological operators. Let me conclude beyond shapes. I've been talking a lot about modeling applications, a little bit of simulation, but a large part of my group is actually doing rendering, and in particular photorealistic rendering. And so one question that arises naturally is, can you use proxies for light transport? As was said before, light transport, it's all about tracing paths of light in a 3D scene and counting the energy brought by those paths onto some sensor in the virtual scene. Now, this is all governed by one equation that everyone knows, the rendering equation, which has several interesting terms. And actually, so far in my group, we have been exploring a lot how proxies can be used to actually model the incoming light in this equation. And we are not the only one. Like a lot of people for 20 years have been looking into simplifying light transport by approximating it locally with some light proxies. Now, interestingly, actually, within the materials, and I'm an algorithmic chief scientist, so I know fairly well how complex the materials can get in production. Within the material, actually, the mesostructure of the geometry can get itself very complicated. The local interaction of light is a complex phenomenon that might benefit from approximation from its actual geometry. More interestingly, many people these days are interested in emissive materials. Emissive materials means you have any map that can actually emit light in your engine, and most of the optimization you did before for your primary light source do not hold anymore. You have to explore the entire scene to actually know where is some light and where you have to compute reflections. Having proxies for that kind of makes sense. And finally, if you look like after like a step further, probably that modeling what's called the planoptic light fields can also benefit from proxies. So basically learning the potential response of the entire scene in any point in the scene to the current lighting condition is currently intractable, and actually geometric proxies can help a lot, modeling empty space and surfaces at the same time in trying to actually approximate the rendering equation, a solution to the rendering equation. Last, I couldn't stop without mentioning machine learning, of course, and proxies here also have a bunch of interest. First, you can compute pretty robust statistics from proxies instead of the original shape. This has interest for some of the applications I've shown before, like 3D search. You can also bootstrap higher level analysis when you just have a couple of primitives to handle. Some algorithms have a superlinear complexity, and that's it. You just cannot bring it to n log n or n square. And basically what you can do with proxies is basically use them as substitute for high complexity tasks and go back to high resolution geometry when you can. Finally, in the context of neural networks, it kind of makes sense to think about proxies as maybe a way to vectorize shape for the input of your networks. And if you go even a step further, for some class of proxies, well, all of a sudden you can start to see this nested hierarchy of variation over the geometry as maybe a way to express layers in a neural network that would be designed specifically for shapes. Okay, a large part of this work is work with my students, Stéphane, Emily, and Jean-Marc, who worked very hard on this, so I'd like to thank them a lot for that, as well as all my coworkers. Here are some papers that summarize some of those things. You can find all the resource, some source code, data, and so on my website. And I thank you for your attention.
All right, thank you, Tamy, so much for coming and for the great talk. We do have time for a couple of questions. We'll do the same exercise as before. You raise your hand, you wait till you get the mic, and then you fire away. I can't see anything. I hope you'll... Oh, there's one right there.
Hey, Tamy, thanks for the presentation. So you had the example for millions of polygons where you simplified that to 1,000 or so. Did you try what happens when you interpolate between the proxy and the original?
So for the bounding proxy example?
Yeah, where you had the sphere with like these tiny, tiny shapes. It was really awful when you had applied the sort of like traditional algorithms and then you tried your own one on that.
So you mean interpolating the proxy toward the high resolution input?
Yeah, like so that? When you bring it from the low resolution back towards high resolution, did you have any experiences there?
Well, it depends which representation you use at this stage. If you stay, for instance, for bounding proxies, if you stay in the volumetric domain, it's a pretty smooth behavior and holes get filled progressively and so on. Obviously, if you already meshed the boundary of the proxy, there is no way you can actually cross-parameterize objects which may have actually different topology. Some people have worked on that, but it's usually not smooth, not regular over time. So I'd say that interpolation makes sense in the volumetric case for bounding proxies. And for sphere meshes, like there is a geomorph continuum between the mesh, the input mesh, and any sphere mesh from it. We actually show it as any mesh is a sphere mesh. It's just a sphere mesh where every sphere has a 0 radius. And when you start from that, you can build a progressive geomorph transformation that goes from high res to low res or low res to high res.
More questions? I have one. When are we going to see proxies in 3ds Max?
Good question.
Whatever the software people are using these days.
So in terms of transfer applications, some VFX studios have approached us to actually use that to control fluid simulations, for instance. Automatic construction of that kind of structure within main packages, I'm not sure. I'm really not sure. I mean, maybe the bounding proxies will make it at some point because it's pretty robust, so robust enough for industry needs. It's pretty new, so let's see how we make it.
Yeah, I know how long it usually takes. But in particular, the use for simulation for no interpenetration, that seems really, really valuable for a lot of use cases, even for real time in particular. If there are no further questions from the audience, let's thank Tamy again for coming all the way here to
Thank you.
And also a big thank you for all the speakers on our graphics track. I think we've seen lots of really different, exciting directions that are happening in graphics and machine learning at the time. So that's the end of the program, and I will now hand back over to Vili to tell you where to go next and so on. Thank you.
Okay. So far, okay, let's do a context switch. Like so far, we had a situation where we had one person singing and about 7 people talking and 400 people listening. So let's kind of like switch it around and go into the mode where I have 400 people talking and singing and maybe 7 people listening. Which kind of means the after party. And the important information is that we have the after party at a nightclub called Maxine, which is on the top floor of the Kamppi department store metro complex. If you do have a black wristband, I hope you all do, you have free entrance. If you still have like a white drinking ticket, you should, because there's no way to use it here. You get a free drink, and the doors open there at 10 p.m. sharp. So we have some time over here, and then it's maybe a 10-minute walk or a short tram ride. And that's it this year. Hopefully you enjoyed. Please come back to us with feedback, whatever you want us to modify for next year's event. And at this point, I think one more round of applause to the organizers, speakers, and sponsors. Thank you. Booyaka.